Hi people. We are going to be discussing chapter 16, which is a shrink fit analysis. And just to remind you that in class and the lab we have discussed two other examples, uh, and one of them was the uh, analysis of a bearing assembly, which I believe was chapter 14. And then we also did chapter 16, which is analysis of a tensile specimen. Uh, I'm planning to do this, which by the way may happen to fit cover two segments because this can be longer than what I thought, and then hopefully there will be another assembly example that I'm going to do before I disappear for some time. Now remember, when I come back, we are not going to be covering assemblies anymore. It's entirely your responsibilities to look at these video clips, go through the book, and make sure that you got the hang of it. Now the problem that we are discussing is this. Basically, it's two rings. The outer one is made out of steel, and the inner one is made out of brass. The idea is to securely position the brass inside of that steel confinement. What people do is they make the diameter of the inner core, for example, that brass that you see there. I'm sorry, you say bronze? I mean bronze. I didn't mean brass. Bronze, a little bit bigger than the inside diameter of the uh, steel opening, and so what you do is then you heat up the steel part so that it expands and its diameter can accommodate the bigger diameter of the bronze, and then you insert the bronze piece inside of that and let it cool. So as the steel cools down, it basically shrinks and embraces that brass or bronze piece, and that's exactly what we mean by either shrink fit or pressure fit, depending on the book that you're using. So, in this particular problem, I'm assuming that the bronze has 0.002 inches diameter bigger than the steel hole. Now, this 0.002 is called diametral interference, but sometimes half of it is referred to as radial interference. This kind of a problem can be solved analytically. And when I was teaching the course, I did actually cover it in the stress analysis course, 92.311. I don't know whether it's done or not. One can actually get an analytical expression for the hoop stress in the bronze. I see that here I'm referring it to as at brass, so this should be bronze and the steel, and they're given by these expressions, both the hoop stress and the radial stress. I'll mention the axial stress in a minute, and then based on the material properties provided, namely Poisson ratio mu, Young's modulus E, and the dimensions of these rings, and the numerator, which is the radial interference, one can find the contact pressure. Now, uh, one thing you should realize, if you plot these two, you'll see that there is a discontinuity in the hoop stress, uh, and it's always the case that when you have material uh, discontinuity, in other words, two different materials, interacting with each other, at the interface, we do have a discontinuity, jump discontinuity, and that's obviously showing up here. Now, the radial stress, on the other hand, is continuous, as you can see that it's a dotted one. The other thing I should point out to you, as far as this problem is concerned, if these rings were actually of given heights, okay, then the problem can be thought of as a plane stress problem. In other words, there is no stress developed in the vertical direction. Or let's put it this way: the stresses developed in the vertical direction are very small because there's nothing that confines this thing from moving in the vertical direction. On the other hand, if you view these things as very long rings, then basically we are pressure fitting a tube, a long tube inside of another long tube. In that situation, you're dealing with a plane strain problem. In other words, uh, there is actually uh, there's actually stresses developed in that length direction. Now, for me, I'm assuming that this is a plane stress problem. In other words, there is no stress in the height direction, and therefore this is a ring pressure fitted inside of another ring. The other thing is that this problem is done in the book, but no planes of symmetry is taken. In other words, it's okay if you do it that way. However, if the problem is given to you on the test, you will be asked to use any applicable planes of symmetry, and in this case you can see what the planes of symmetry is. First of all, there's infinite number of planes of symmetry. One of them is definitely halfway between the top face and the bottom face. That's obvious. That's not hard to see. And the other two that we can take, any two radial planes, in other words, any like a segment, any segment, 90-degree segment, 30-degree segment, any segment is also acceptable. So that's one difference between what I'm going to do and what's done in the book. Okay, so I will take a segment, but if you're interested on how to do it as a full structure, which is actually harder because it's going to be tougher to, you may have issues with restraining the object from rigid body motion in the vertical direction, you can look at the book. All right, so I will use the same dimension that's in the book. So let's go to Catia and create the part or the assembly actually. So let's see now. Insert, new part, in there, and let's call this thing. Let's do the outside one first. So let's rename this thing to be steel and steel. Say OK. Let's make the steel. On the XY plane, which is just for convenience, I will draw a sector of that structure. So this is going to be my, well actually let's do a sector like that. And I'm going to put a dimension here, so that is exactly what we want. Okay, so let's see, a line from here to there, and a line from here to here. Let's give these things some dimension. This outside one and this inside one. The inside one, according to the book, is 2 inches. And the outside one is 2.5 inches. These are the radii, 2.5 inches. Okay, the only thing is that I have to close this thing. So what we can do is this point, control that point, and you make it. Actually, let's start this point. Control this point, and we make it coincident. Or you could have trimmed it, by the way. Okay, good. Now I'm going to exit this thing, and I'm going to pad it of half the height that's specified in the problem. If the height in the problem, let's see, I'm looking at the book to see if the height is given there. I think it is given. The height is let's see. I'm not sure whether the height is specified in the book or not. It probably is, but I don't have the time to go and find out what it is. So if let's hypothetically say the height is uh, 3 inches. Okay, then I'm gonna pad this thing by 1.5. Instead of using the saw and cutting it and things like that, we're going to actually, you know what, let's make this thing how about 0.5. Okay, so the actual problem in the actual ring, the height is 1 inch. What we are doing, because we are taking planar symmetry, I'm taking half the height, which is 0.5. Okay, good. So this is made out of steel. We might as well apply the material property on it. So it's going to be metal out of steel. And by the way, I'm not going to change the values, but if you want, you can always go change the values of in this by double clicking on this. Double clicking on this steel property, you select the analysis, and you can put any numbers that you want for Young's modulus, Poisson ratio, etc. But I don't want to do that. Incidentally, while we're here, let me change the color of this. So right click, properties, graphics, and I'm going to change this thing to say yellowish. Okay, good. Good. So look, don't forget to save. We do a file save management, file save management, save as. Okay, on the desktop, we create a new folder. We give it a name, shrink fit, and say OK, and save everything. Good. Now we insert the second part. So insert a new part in there. Say no, and I'm going to change this thing to bronze. So we're going to change the name of the part and the instant name to bronze. And bronze. Okay, let's make it. Double click on a convenient plane, the XY plane. I will sketch. Now, in the book, I have actually, when I made the part, I made it look exactly with the bigger dimension. In other words, what I did, I made the radius of the outside circle of the bronze to be 2.001, because that's exactly the way we actually want this part to be. However, what I'm telling you is that in order to do this analysis, it is not necessary to make the parts of different sizes. In other words, I can still make the outer radius of the bronze to be 2 inches, not 2.001 inches. However, later on, when it comes to Catia asking me what is the radial interference if you want to do shrink fitting for these parts, I will say that the interference is 0.001. In the book, the outer radius is made to be 2.001. What I'm going to make is 2.0, okay? And it will not change the analysis. It obviously there's some differences, but it's perfectly acceptable either way. So let's go here and create what we want. In other words, I'm going to project this because the radius is the same, 2.0. This is what I decided to do. And then I'm going to make the other one. The inside radius of that thing was, what was it? If you look at the paper, the inside radius is of the inner hole is 1. Okay. So first of all, let's clean this up. Let's see. From here, let's hide this guy. Okay, from here to here, and then from here to here. I'm gonna have to do a little bit of a cleanup here, so I'm gonna do a quick trim. So this is gonna go. All right, let's wait. This is thinking. Okay, this is gonna go. Oh wait, it'll work. This is why it's so important to save things in case, you know, this happens. Good, it did work. And then this one, and this radius, obviously that radius is already 2. I know that because it was projected from the steel part. And this radius, I want to make it a 1. Good. Now we exit this thing, and we pad it by half an inch, just like the steel part. So you can see that we pad this. Where's the pad? Pad this by 0.5. There. Okay, we make this thing out of bronze. So apply material bronze on this part, and we say okay. Save everything. Let's actually save the whole let's save the whole product because I'm doing it the lazy way. Good. Now we're going to move to what is that? Analysis and simulation, generative structure analysis. Okay. Well, you can see that the 2 parts have been meshed because we're dealing with an assembly here. Catia, as soon as it sees a solid object, it's going to mesh it. Okay. And if you want to see the mesh, right click, mesh visualization. There it is. Okay. And notice that there is an interface here. As a matter of fact, to convince you, I can change the color of, say, the steel elements. So properties, I'm going to change it to a different color. Instead of this, maybe yellow. And you can see that. And at the interface, you can see that the nodes do not line up. Okay, good. By the way, it is possible to make sure that they do line up, but it's irrelevant to our problem. Deactivate the mesh here. Now, these are planes of symmetry. So some of them are planes of symmetry. So surface slider on this face, and on that face, and the bottom, and this bottom, and this side, and that side. These are all planes of symmetry. The top is not. The top is not a plane of symmetry because this ring was 1 inch thick. I took half of it, therefore the top is free. All right, good. Now we have to create a connection. So connection, I hide this thing between this face as the first component, and for the second component, this corresponding face of the bronze part. Say okay. Let's bring it in the front, and you can see a connection has been created right there. I see this black dot. That's what it is. When I put the cursor on that black dot in the tree, the connection lights up. What we want to say now is that this is a pressure fit or a shrink fit connection. So look at your face to face connection. There we are. You have used the second one, which is contact. You have used the third one, which is fasten. Hop over 2 more. Second one from the left, it says pressure fitting connection property. So you click on it, it says, where is your support? Well, obviously the support is this connection that I created. Notice that it puts this thing that looks like something being squeezed inside of something else. And there is the radial interference that you have to put in there. Remember, this has the radial interference of 0.001 inch, and there it is. The only reason it knows what the value is, I didn't type it in, is because when I did the problem, you know, yesterday or last week, I don't know, I put up the correct value, 0.001. Now, even notice that the way I made the parts, there were no interference in the parts that I made. But still I do this. Even in the book, when I create the part, which is a little bit bigger, by this much bigger, I still do the same thing. So we say okay, and hopefully we did not forget anything. We're going to run it. Let me run this thing. It's complaining about the mesh. We know that at the interface there is you need a finer mesh. It's complaining that, you know, your mesh is probably not good enough and things like that. So let's look at the stress distribution. There is something I see here that I don't like, but anyway, we'll see that. First of all, let's look at the different rendering. There it is. And I certainly do not like what I see here. We may have to go and fix this thing, because I see that here we have a big component of stress showing up, and that's unrealistic. Okay, and as a matter of fact, what I also see is that this is not symmetric. I mean, you can see that it's supposed to be symmetric, unless my eyes are playing a trick on me. Since I'm running out of time, what I'm going to do, I'm going to stop this video clip, and going to go back to it and try to fix it. This definitely is not right. Okay, so let me stop this.